On to linear and exponential functions 4.6. Alright, so this first part we're going to compare linear and exponential models. Okay, so we're going to fill out different parts to them and kind of look at them side by side. So here's our functions. Okay, so what type of growth do we have here? Well, 3 times x, that's arithmetic, right? We're adding 3 each time. It's plus 3, plus 3, plus 3, however many times. That's what the 3x is telling you. Whereas 3 to the x is 3 times 3 times 3. So it's geometric. Even though it's the same number. Oh, dang it. I might be jumping ahead. I think those should have went down there, huh? So type of growth would be 3 plus 3 plus 3. You could also call it linear. Type of growth, 3 times 3 times 3. You could also call that exponential. And then the sequence was arithmetic and geometric. So if we make a table of values, let's go 0, 1, 2, 3. So in this first one, we start at 4. Then we're adding 3 each time, right? So 4, then 7, then 10, then 13, and so on. For the geometric, for the exponential pattern, we start at 4 still. This time we're multiplying by 3. So we have 12, then 36, then 108, right? 36 times 3, 18, 9, 10. Yeah, 108. So notice we've got the same starting points and the same number, but because we're multiplying or adding, that changes things, right? Alright, so what's the rate of change on number 4? Well, we're adding 3 each time, right? What's the rate of change on the exponential? We're timesing by 3. So then we would graph each one. So you can kind of look back to your table, 0, 4. So 0, 4 would be right about there. Then up 3, 1, 2, 3 to the right 1. Up 3, 1, 2, 3 to the right 1. And so on. Right, that slope, that rate of change stands for the slope on that linear equation. So then it would go like that. Okay, now if we're talking about the exponential, we start at 4 still, and then we multiply. So we go up to 12, and then we're pretty much out of luck, right? So it looks something like this. Like, actually, like this, growing very quickly. Okay, the y-intercept, that's our starting point, 0, 4 for both of them, right? Going back to here. It's our y-intercept, here, here, okay. Alright, now number 7, find the y-intercept for the following equations. Well, 3 to the x plus 0, so its y-intercept would be 0, 0. 3 to the x, that'd be like times 1, so it would be 0, 1. Explain how you can find the y-intercept of a linear equation and how that is different from finding the y-intercept of a geometric equation or exponential. Well, if we look kind of at that, it's the number you're adding, right? Number being added to the growth. That would be the linear, whereas with the exponential or geometric, it's the number multiplied by the growth. And you could easily find them just by plugging in 0 for x too. You know, that's another way. Y equals 3 times 0. Y would equal 0. Y equals 3 to the 0. And if you didn't know, anything to the 0 power is actually 1. So that's a second way you could find it as well. So either one of those would work. Alright, now we're going to take a look at some arithmetic and geometric means. Okay, so they want us to, it'll be like the first, second, third, fourth, fifth term. Okay, so we've got 1, 2, 3, 4. 1, 2, 3, 4. So remember, with arithmetic, we go the last minus the first. That gives us the total difference. And we divide that by the number of times we have to add to get us what number we add by. So this is where you'd want to use a calculator, right? So 324 minus 4 gets us 320. Then we divide that by 1, 2, 3, 4 to get 80. So we're adding by 80 each time. So that'd be 84, 164, 244, and then 324. Now, for the geometric, remember that the geometric is the last divided by the first. That gives us our total quotient. Then we take the root of that total quotient of how many jumps, right? And that gives us our number we're timesing by. So I'd go 324 divided by 4 gives me 81. Then we take 1, 2, 3, 4, the fourth root of 81, which would give us 3 when we type it into our calculator. So we'd go the fourth root of 81. So you'll need your calculator. So we're timing them by 3 each time. So that'd be 12, be 36, that would be 108, and 324. Okay, so that's just kind of looking at that comparison between those. So once again, arithmetic, 48 minus 3 would give us 45, divided by 1, 2, 3, 4. 45 divided by 4 would give us 11.25. So 3 plus 11.25 would give us 14.25 plus 11.25, 25.5, then 36.75, and last 48. Okay, now let's do the other one. 48 geometric divided by 3. So just some good practice. Gives us 16. Then we've got 1, 2, 3, 4. So the fourth root of 16, which I believe is 2. Let me double check that. The fourth root of 16 is 2. So we're times them by 2 each time. So 6, 12, 24, 48. So you see how it's a different pathway to those same numbers. Okay, let's keep at it. So negative 10 minus negative 6,250 gives us, remember that's like plus, so it ends up being positive 6,240. 1, 2, 3, 4, so divide that by 4. We are adding by 1,560. So negative 6,250 plus 1,560. So negative 4690. Oops, dang it. Negative 4690 plus 1560 is negative 3130 plus 1650. Oh my goodness, 1560. Having an issue with my calculation. 1570. One more time, negative 10. Alright, then the geometric version, negative 10 divided by negative 6,250 would give us negative 10 divided by negative 6,250 gives us 0.0016. If I do it in the calculator. As a fraction, that's 1 over 625. Okay, doesn't matter which one you use. Then we've got 1, 2, 3, 4, so we take the fourth root of these. Which, when you're taking a root of a fraction, you can separate it. Take the fourth root of the top, the numerator, and the bottom, the denominator. So the fourth root of 1 is 1. The fourth root of 625 would be 5, so it's really 1/5 that we're timesing by. In other words, we're dividing by 5. If we did it decimal-wise, it would be 0.0016, which would give us 0.2 which is the same thing as 1/5. So whether you times it by 0.2 or by 1/5, same thing. Negative 6,250. Do you multiply it by 1/5 or by 0.2? We keep it going. So be 12, negative 1250, negative 250, then negative 50, then negative 10. Alright, so these ones aren't too bad, huh? So erase that. Alright, let's keep on going. Negative 0.75 minus 12. So it doesn't matter really what numbers you're dealing with. 1, 2, 3, 4. You still treat it the same way. And this is where it's handy to have a calculator, because 2.8125 is not a fun number to have to add. But I go negative 12 plus 2.8125. We get negative 9.1875. Then we do it again, plus 2.8125. Gives me negative 6.375. Do it again. Negative 3.5625. Do it again. Negative 0.75. So kind of funny how that turns out, but works us out. So negative 0.75 for the geometric divided by negative 12 is 0.0625. We'll take the fourth root of that. Gives me 0.5. So 1/2. So if I put 0.0625 as a fraction, that would have been 1/16. So we take the fourth root of the top and the bottom, would have gave us 1/2, so 1/2. So timesing by 1/2 or 0.5, same thing. So negative 12 times 0.5 is negative 6, then negative 3, then negative 1.5, then negative 0.75. Alright, so now let's take a look at some comparing of these functions. So notice this table. You've got the x value, the output for the f function, the output for the g function. So the f function here looks like this one, going at the curve, and the g of x is the linear one. So exponential and linear. So here's the exponential equation, the linear equation. Okay? So then it wants us to look at which one do we think is growing faster, let's see. Compare the rates of change of each pair function by identifying the interval where it appears that f of x is changing faster and the interval where it appears that g of x is changing faster. So interval, remember, is just the section. Okay, so there's our y-axis. There's our x-axis. So it looks like to me that g of x is growing quicker about, from this portion on. So that's like 0, negative, or positive 1, positive 2, even negative 1, so I could go negative 1, 0, 1, 2. Then, from this section on, it appears that f of x is growing quicker. So, if we took a look at those, that would be 3, 4, 5, and so on. But it looks like this is kind of where things change. So now, there's a few ways we could do this. Okay, probably the easiest way is to simply look at the functions and at those x values, find the y values. I'll show you both ways. So if I go to negative 1, well, it appears that that one, they're both kind of, they didn't really give us a good number, right? So, but if I had to guess, g of x would look like it's at 1/2, and f of x might be, negative 2/3 or something. The way we can double check is plugging it in. What's 1.5 to the negative 1? If we put in negative 1 for x. Well, I use a calculator. 1.5 to the negative 1 gives me, 2/3. So f of x would be 2/3 at that. if we look at the y-intercept, pretty easy to see that f of x is here at 1. Okay? And then it's hard to see any other easy numbers except up for this one of f of x, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. So at 4, f of x is at 5. To find the other ones, we just simply plug it in. 1.5 to the first is 1.5. Okay, 1.5 to the second is 2.25. 1.5 to the third, so I'm just plugging the numbers in, 3.375. To the 1.5 to the fourth, it's basically 5.06. It's actually a longer decimal. And then 1.5 to the fifth is 7.59. We round it up. Okay, now let's do g of x. So g of x is probably easier to see. At 0, it's up to 2. At 2, it's up to 3. And notice it's grown by a half, right? So we're adding a half each time, so that'd be 2.5. Be 3.5. And then 4. Then 4.5. So this would be 1.5, right? If we didn't know, we could plug it in. 1/2 times -1 plus 2. Give us -1/2 plus 2 is 1.5. Okay? So now, we already said that it looks like g of x was bigger on that point. Is that true? Yeah. See how those numbers are bigger? Okay? Then after 2, well, I mean even up to 2 it's bigger. Then after 2, we can see that f of x is bigger, which would represent that part. Alright? So that's what it wants us to do on the rest of those ones. So taking a look at it, same idea here. So, we've got x, f of x, and g of x. So f of x again is the exponential. This time it's going down. G of x is the linear. So now it looks like we'd probably want to choose numbers from like negative, let's see, here's our x-axis, or y-axis, well, here's our x-axis. So it looks like which one's going down quicker? Well, f of x, it looks like once we hit this point, it's going down quicker, right? So that would be at 2, okay, and beyond. Whereas g of x looks like it's going down quicker, you know, to the left. So maybe like -2, -1, 0, 1, 2, 3, 4, to give us an idea. And then we can either plug numbers in or try to figure it out from the graph. Now I'd probably try to figure out from the graph first. So there's my, again, there's our x-intercept, and there's our y-intercept. So it looks like f of x at 0 is 0. And then at 1 it looks to be -2. And then at -2 it looks like it's clear down there at -8. Okay. Let's double check those. -3 to the first plus 1. -3 to the first is -3 plus 1 is -2. -3 squared plus 1 is -9 plus 1 is -8. Yep. So -3 to the third plus 1, -3 to the third would be -27 plus 1 would get us -26. Then -3 to the fourth plus 1, that's -81 plus 1 would give us -80. Now going backwards, -3 to the -1 plus 1. So use my calculator here. -3 to the -1 is a fraction. -1/3 plus 1 would get positive 0.666, so 2/3. Okay, if we did it with -2, -3 to the -2 plus 1 would give us 8/9. So some ugly fractions, right? Alright, now looking at the g of x, negative 2x minus 2. Pretty easy to see at 0, we're going to start at negative 2, right? Using that y-intercept. And then we're subtracting 2 each time. So negative 4, negative 6, negative 8, negative 10. Going backwards, that would be 0, right? At negative 1. So linear, much easier to move by, right? Positive 2. So once again, we have bigger numbers until we get right here. Then once we get past that number 2, then f of x is growing quicker. Alright? Now let's take a look at 15, do the same exact thing. Okay, so we've got our x-intercept, our y-intercept. So it looks like the g of x, okay, it looks like it's going to keep going up quicker now this time, doesn't it? But will it? So maybe we should start off the graph here at like, 3, 4, 5, 6, 7, 8, 9, 10. Let's go to 10. So if we look at g of x, it's just 8 times x. So our 3, 8 times 3 would give us 24, right? So then we're just adding 8 each time. So 24, 32, basically count by 8, right? 40, 48, 56, 64, 72, 80. Let's see where that gets us. And 88, because that one's easy. So now, let's look at 2 to the x. Okay, so 2 to the third would be 2 times 2 times 2, which is 8. And then we're timesing that by 2. So 16, 32, 64, 128, and so on, right? So we can see that even though on the graph it looks like g of x is always going to be growing bigger, it only happens up until 5. So everything be earlier, but right about here the interval would go, this way. Whereas that exponential equation, f of x, starts to jump up pretty quick. Alright, so now we're going to write the explicit equation. So remember, for linear, the explicit equation is y equals mx plus b, but we often put the growth first and do b plus mx, right? Whereas the exponential is a times b to the x. Okay, so let's look at this first one. How is it growing? Negative 4 to negative 11 to negative 18. Are we not adding, subtracting 7 each time? So if we're going backwards, because that would be 1, we need to get up to 0, right? So going backwards, that would be a positive 3, that would be a positive 10. So we'd go y equals 10 minus 7x, or y equals negative 7x plus 10. Same thing. Okay, the second one, 2/5 to 2, so we're timesing by 5, right? So our 0 is 2, so we'd go y equals 2 times 5 to the x. Okay. Here's our y-axis, there's our x-axis. So if we're looking at 18, it looks like it's linear. So there's our y-intercept, right, at 2. Then we go down 2 to the right, 1, 2, 3, 4, 5, 6. So negative 2 over 6, which would become negative 1/3. So we go y equals negative 1/3 x plus 2, or y equals 2 minus 1/3 x. Same thing. Okay. Now, for 20, looks exponential. So here's our y-axis. This is probably our x-axis, but I'm not really sure. But I'm just going to say it is. So here, we're not sure where that is, right? But that, at 1, we're up to 1. And then at 2, we're at 2. And at 3, we're at 1, 2, 3, 4. And 4, we're up to 1, 2, 3, 4, 5, 6, 7, 8. So we can see 1 to 2, 2 to 4, we're timesing by 2 here, right? So if we went back to 0, it would end up being 1/2. So y equals 1/2 times 2 to the x. Okay, number 12, we've got a point right there. We've got our y-intercept right there. 1, 2, 3, 4. So negative 4. We're going down 1, 2, 3, 4 to the right 1. So by equals negative 4x minus 4. Alright, now if we're graphing solutions of systems, so we graph the two lines and then we just find where they intersect, right? So there's our y, that was a crappy y-axis. There's our y-axis, there's our x-axis, y-axis, our x-axis. So this first one, y equals negative x. That'd be like plus 0, right? So we start at 0. Negative x is like negative 1, so we're going down 1 to the right 1. So like this. Or the opposite direction, right? So there's that line. There's our first one. And our second one, we start at negative 4. And we're going up 3. So 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. Honestly, that's enough to draw it. So, where does it intersect? At 1, negative 1. There's our solution. Okay, if we look at the next one, y equals 6. We go up to 6. On the y-axis, we draw our horizontal line. For the next one, we need to turn it into slope-intercept by subtracting 2x. So we'd get y equals negative 2x minus 6. So we start at 6, 1, 2, 3, 4, 5, 6. And we're going down 2 to the right 1. Or up 2. Erase that one. Or up, oh my goodness, what did I do on that line? Down 2 to the right 1. Or up 2 to the left 1. We see where it intersects right there, which is at 1, 2, 3, 4, 5, 6, negative 6, 1, 2, 3, 4, 5, 6, negative 6, positive 6, and that's our solution. Okay, for the last two, same idea. Let's draw our y and our x, our y and our x. So start at negative 2, then we're going up 2 to the right 1, or down 2 to the left 1. There's our first line. Our second one, we'd subtract x, right? To get 3y equals negative x plus 15. Divide everything by 3. That would give us y equals negative 1/3 x plus 5. So go up to 5. And we're going down 1 to the right 3. We can see where that intersects, right? Right there at 1, 2, 3. 3 for x. 1, 2, 3, 4. 4 for y. Alright, the last one, 25. That one looks kind of crazy, doesn't it? So let's give ourselves some space. So we'd subtract 3 to get y equals 6x minus 5 for the first one. So let's draw that x and y axis. Oops, again. So we start at negative 5. And we're going up 6 to the right 1. Oops. So there we go for that one. Okay. Now for the last part, we got a lot of work to do here. Y minus 2x plus 1 equals, first I multiply, 4x minus 4. So we subtract 1, which would give us minus 5. Add 2x, which would give us 6x. So we get y equals 6x minus 5, which is the same thing. And remember, when they're the exact same thing, we call that infinite solutions because they're overlapped. They're always intersecting. So there we go, guys. So quite a few problems there, but some good stuff to go along with what we've been doing.